Hello everyone, good day. This is Siagia Karki from UT Austin. The topic of my presentation today is transport in scandium nitride magnetic tunnel junctions using first principle. This work is done by a group of people here at UT Austin led by Professor Gina and Incorvia. It's done in collaboration with Dan Marshall from Arizona State University. I'm going to go over a brief outline of my presentation. First, I'll talk a little bit of motivation and the state of art of magnetic tunnel junction, and then move on to scandium nitride and why we picked this material. After that, I'll talk a little bit about our results and then move forward to concluding the presentation. So amorphous aluminum oxide was the barrier material first explored, and it resulted in incoherent tunneling of the various block states, which therefore resulted in an MR ratio of less than 100% at room temperature. Further moving on from aluminum oxide was magnesium oxide, which was crystalline in nature that resulted in a dominant tunneling of fully spin polarized delta-1 block states. And in theory, this predicted an MR ratio of way higher than 1000%. There are several advantages to why MgO has been the leading tunnel barrier for over decades now. When deposited, it's crystalline in nature, and it has very different electron block waves in parallel versus anti-parallel states. Therefore, it results in a very high TMR, as I mentioned in previous slide, of about 1000% in theory, and when measured, it was able to get up to 600%. Although MgO is the leading tunnel barrier, there are several challenges and limitations of why MgO is restricting for wider applications. One of the very important challenge in MgO junctions are that MgO has a very high band gap. And this band gap results in the barrier thickness less than 1.5 nanometer to have an optimum RA product. And when this is less than 1.5 nanometers, there's a lot of pinholes in these barrier regions. Also, MgO is transparent in nature, and with limitation of very low barrier region, it's very hard to grow and pattern these compared to other emerging memories. Therefore, it's delicate for high activity factor applications such as neuromorphic computing. These challenges and limitations of MgO is what led to exploration of scandium nitride. Scandium nitride has a similar rock crystal structure to that of MgO, but it has an advantageous narrow band gap, which could possibly lead to a thicker barrier with low RA product. Also, there is a lot of dead oxide layers at the interface between MgO and the electrode. So nitride film could possibly avoid those dead oxide layers. Also, nitrogen diffuses better during annealing as well. Further on, we moved towards the electronic band structure of scandium nitride, as shown here on the plot. As DFT underestimates band gap, we had to use a correctional potential to match its band gap with experiments. We used a range of Hubbard correctional potential, and we found that 4.5 eV was optimum that needed to be added to 3D orbital of scandium to get a band gap that matches with experiments. Further on, we looked at the symmetry resolved bands for SCN and MgO. On the left is SCN, where we can see that the real K-space is sandwiched between the two imaginary K-space, and we find delta 1 bands and delta 2 prime bands with a very low decay rates at delta 1 band being at gamma point and delta 2 prime band being at X point. In parallel, we also did our symmetry resolved for MgO, and as expected, we see a low decay rate of delta 1 band at the gamma point. All of our calculations are done in parallel with MgO so that we can validate our results for scandium nitride. If you want to look at more detailed work, this is our paper on tunnel magnetic resistance in scandium nitride magnetic tunnels junctions using first principle, which is under review at the moment. Now moving forward to FESCN junctions. We created several SCN junctions, layer systems. We did 3, 5, 6, 7, and 8 layers sandwiched between 2 ferromagnetic Fe electrodes. The scandium nitride region was rotated by 45 degrees so as to match it with the lattice constant of iron. The calculations, the molecular dynamics was done in VASP in the plane wave conduction in Quantum Espresso. Quantum Espresso uses a Landier particular formalism that depends on the transmission probability and gives you the conductance value. So we looked at several K-resolved transmission probability for our junctions. The top A, B, C, D is for the 6-layer SCN, and the bottom E, F, G, H is for 8-layer SCN systems. Each one showing the up and down channel in the parallel configuration and up and down channel in the anti-parallel configuration. As you can see in figure A, that there are a lot of transmission around the gamma point and also around the M point, which is expected because we have a direct gap around a gamma point and also an indirect gap in SCN systems. And we see that these are actually filtered out in the down channel in the parallel configuration. Similarly, we can see that on 8-layer system, we have more around the gamma point. This is due to the bending of the conduction bands. And we see those get filtered out in F. Similarly, we did a K-resolved transmission probability for MGO junctions to validate our results. We saw in the parallel up channel, there is a high transmission around the gamma point, which is filtered out in the parallel down channel. And similarly, we see a very low transmissions on the anti-parallel channels. Further on, we looked into the scattering states versus Z for several K points for different layers. This is an example of 6-layer system. On the left is the majority spins, and on the right is the minority spins. The in-between layer is the scandium nitride layer sandwiched between Fe left and Fe right. Fe left is from 0 to 8, and Fe right is from 24 to 32. We see on the majority channel that there are delta 1 and delta 2 prime, whereas when we look at the scattering states for the minority spins, we see that these gets filtered out. This is an essentially important point, as we can point out and validate that scandium nitride can do symmetry resolved filtering mechanism for its majority and minority spins. Similarly, this is one picked layer 8 at K point, a different K point where we have higher transmission. We see that the major transmission is due to delta 1 at this point, which gets filtered out on the minority spin. Similar to the previous slide, this again validates our point as scandium nitride is an efficient spin filter. Further on, we looked at the several parallel, anti-parallel conductance values and also the MR ratio of the junctions. We see we get a very high MR ratio of about 12,000% for a 6-layer system and as low as 100% for a 5-layer system. So we wanted to further study why there is a variation in our MR ratios. And we think one of the reasons could be due to the lattice mismatch between iron and scandium nitride. So the higher lattice mismatch actually causes dislocation at the interface and break the crystallinity. So we looked at the displacement of the Z from for our atoms from the barrier region, and we see that for the even layer systems, it's uniformly displaced negative and positive direction, and it lets the lattice relax more, which is expected in experiments too. Therefore, it could probably describe why we see higher MR ratios in the 6 and the 8 layer system compared to our odd systems. We do know that the lattice mismatch is very high for FE-SCN junctions, but Fe was a choice of material because it's the electrode material being used. And in this work, we just wanted to look at the filtering mechanism of scandium nitride. We are further exploring a better choice electrode material for SCN junctions. With that, I would like to conclude my presentation. by saying that SCN is a new exciting material for MTGs where there is very low alternative barrier materials. It is exciting because it has a lower band gap, which could possibly lead to a thicker barrier with low RA product. And its MR values are very comparable to that of MgO junctions. And we do see that delta 1 and delta 2 primes symmetry filtering with low wave function decay rates. Although Fe is not the optimum electrode material for SCN junction, further work needs to be done in exploration of new materials for SCN. This is our team here at UT Austin working on the project. And I would like to acknowledge Texas Advanced Computing Center for its computational resources, Center for Dynamics and Control of Materials, NSF MERSEC for the funding, and Scandium National Labs also as our collaborators. Thank you for listening. I am more than happy to take any questions.